So like Patricio said, my name's Curtis Bell. I did my master's in the CCWJ at the same time Darren did. I currently work for Iris MDT as an asset integrity specialist. So I do a lot of welding engineering support for various clients, and then I also do a lot of failure analysis and then also pipeline integrity work. Iris MDT as a whole, we're primarily an inspection company. We got offices in Canada, the US, the UK, and Australia. And we also provide like engineering services. So our Edmonton office is pretty much the only one that does a lot of failures, although we do some in the UK. And then Australia, they do a lot of power generation and stuff like that. So we're a pretty mixed bag company, but there's a lot of interesting stuff going on. So as advertised, I'll be talking to you guys about pressure codes and welding standards. And in this context, pressure codes, like whenever you get into pressure welding, it's basically, it's anything that retains pressure that you can't walk on, drive over, or live in. So the distinction comes, like you can build a staircase to whatever structural code or whatever governing documents, building codes it applies. As soon as you want to weld it to a pressure boundary, to something that holds pressure, then you have to start to invoke some of these pressure codes. So we're going to go through it. So there's good and bad news. The bad news is there'll be a little bit of repetition. The good news is my presentation will be shorter, and I've punched it up some pretty fancy animations, so stuff's going to come flying in from the bottom, from the side. It's going to be wild. So we're going to start off, we're going to do a bit of a deeper dive into ASME 9 and just sort of how you approach things from a pressure code standard using ASME 9 as the template. There's other pressure codes, there's ISO ones, but for North America, predominantly we rely on ASME, and then pipelines are their own separate world. We'll briefly talk about pressure code structure, because again, it covers a wide range of applications and it's a little bit different. And then finally, we'll get into something that's hopefully a little bit more interesting, which is the code interpretation, which is just picking and choosing specific examples. Like pressure codes cover a whole wide range of things, and they can get horribly complicated. So the whole point of this is not to make you an expert. Like that takes a long time. There's literally week-long courses that are just on ASME 9 or ASME 8 or B31.3. So this is just more to give you a taste that's a mile wide and an inch deep. So when you encounter it for the first time in the industry, you're like, oh yeah, wait, there was more to this. I need to go back and double check. So as Naren said, the code is broken up into 4 sections. The 100s are basically, the first section is, again, how you test things. It outlines how you do a tensile test, what the acceptance criteria are. If you're doing a visual inspection, what's the acceptance criteria for a macro etch, and so forth. Section 2, or Article 2, is for the WPS PQRs, limitations, requirements. 3 is for the welder qualification, and then 4 is basically your welding data. For this portion, we're just going to concentrate pretty much on 2 and 4. The welder qualification, all that kind of stuff. It's all just variations on a theme. So the main difference between sort of pressure codes and regular sort of structural codes or any other kind of thing is it's a 5-step process, but you have to understand the code of construction. The code of construction literally drives absolutely everything else. So the code of construction will inform your welding process, which includes, it's more than just your MIG, your TIG, your stick. It's also temper bead, whether you're doing corrosion-resistant overlays. It'll specify material grades, thicknesses that you can use. And then you also really need to understand the intended service, because that'll change your welding parameters and how you approach it. So the 5-step process is basically, understand the application, develop a draft procedure, make a qualification weld, test the qualification weld, write the WPS. Unfortunately, in our industry, this becomes an iterative process. So they'll test a qualification weld, it fails, they turn a dial, weld another one, test it, it fails, turn a dial, weld another one, test it, pass, rate the WPS, what have you, or way to go. So that's why Patricio is building a scaling thing and a bunch of other stuff to try and make it less of an iterative process and less of a time sink and money sink. So as Naren again said, the WPS PQR needs to list all of the essential and required supplemental essential variables that are used in welding. And again, this definition for codes, when you talk about supplemental essential, that applies to any time that you require impact toughness or notch toughness, which again is governed by your code of construction when that comes in. So the WPS, again, basically the Coles notes is it specifies the allowable range of variables that you can use as defined by the code or the guiding documents. Again, you have ASME 9, and then you have the code of construction. The PPR defines what was actually used during the qualification. And then lastly, sort of listing or recording of non-essential variables is optional, as Naren said. For the most part, if you're ever involved in this, especially on the PQR, just record them, because if there's a code change or a specification change, if you don't have that data recorded and certified, it's gone, you gotta start over. If you have that data in there and it can inform them, then it just becomes a paperwork exercise and you can update, resubmit, and you're way to go. So for each of the welding processes, including special processes, tube-to-tube sheets, corrosion-resistant overlays, any of that kind of stuff, ASME in the QW250 lists all of the essential variables, supplementary essential variables, and provides basically a summary of the brief of variables, they call it. So these little, I think those are sized, basically to denote a change, and then, you know, you got a deletion or an addition or a deletion or a change, an increase, and decrease. But if you want to know specifically the details of each one, then you got to follow basically each clause and each clause that's referenced for each one. So the draft procedure, as I said before, is intended. Apologies. It's intended to ensure that you cover the range of applications. So for example, if we wanted to weld an NPS 8 skid 80 piping. So I should say this right now, sorry, I live in the world of pressure piping, so if I throw out some jargon that you guys don't know or understand, just stop me, ask what it is, because I assume that everyone knows everything that I know, so I just shortcut. So schedule is just basically, NPS, does everyone know what that is? It's a nominal pipe size. So when you say NPS 8, it's a nominal pipe size, and then that means it has a standard diameter, and that's for mating components. The schedule, again, is just a standard thickness for the components. So an NPS 8 skid 80 has about a 1/2 inch nominal wall thickness, or 12.7 millimeters. So they have big tables of charts for all these, but anyways. So if we need to do that, we need to figure out first, when we're building our sort of draft procedure, we need to select a coupon that'll cover it. So if we just focus on thickness and no other essential variables, we go back to QW255, assuming we're using the gas metal arc process, and then we can go, okay, here, so we need to go look at QW403.8. So we go there and we find, hey, it's right there, that's handy, tells us which table to go and look up. And here enters the pain in the ass part of ASME codes, is everything is fragmented. So basically, it tells you here, and then it says, okay, go to this table. But this table might be modified by this. So every time you go into a code or an ASME code, it'll reference something else. And then those other references might also reference something else. So it's basically a tree that you gotta follow all the way down to the roots. But anyway, so if we go to the source, the first one, QW451, you see how that floated in from the bottom? Told you it was gonna be a while. So, and anyway, we can see here, you can select your coupon thickness. It gives you your minimum qualified thickness, your maximum qualified thickness, which in this case is 2 times your coupon thickness. Goes through, this table also defines a lot of the tests you need to do for almost everything, with the exception of special processes. It's 2 tensiles, 2 bends, or sorry, 2 face, 2 root, or 4 side bends. So the important thing to note that differentiates sort of ASME pressure piping, pressure vessels versus pipeline, is whenever they talk about tension tests, the acceptance criteria is always based off of the UTS. And that's because the design criteria for ASME, everything's based off of the ultimate strength. Their allowable stress is everything, whereas when you go to the pipeline world, most of it's designed off of the yield strength. So when they talk about tensile tests, they generally want the yield strength as the pass-fail criteria, which is 0.5 elongation under load method is generally what they use. And again, as I said, there's notes that are called out, so then there's further modifications. So if you're designing this and you're doing your draft procedure, you'd have to take a look at each one of these to make sure it applies to your process, or it doesn't. So if we go back to that first one that was called out, the 403.8, We can see their reference clause was for dissimilar base metal thicknesses. If we're not using that, we don't really care, but then we still need to go back to our process and double check for a range of essential or supplemental essential variables. So say we're using the short circuiting arc process. We can see here, oh, sorry, I cut off the top of the table just for clarity, but we can see here that it's a supplemental essential variable, an essential variable. So we go look at that and it says, okay, well the short circuiting arc process is now limited much more stringently than that 2T that we saw in the QW 451. And this is a result of the actual process itself. Like, have you guys gone through short circuiting transfer modes for a MIG? So everyone knows it's a high deposition, low heat input process. So the problem with that is they found in industry, the very hard way, that when you use that process because of a low heat input, if you qualify on a thin coupon, then you go to a thicker coupon, it's more prone to a lot of like severe weld defects, sidewall lack of fusion, unacceptable root profiles, cold shafts, just rejectable indications. So much so that they wrote it into the code that if you qualify on something that isn't sufficient to get that cooling rate to steal the heat, then you're limited to 1.1 times the thickness. Yeah.
All those fancy transitions catching up.
Yeah, pretty much. Anyways, so, or as a design and service considerations, so we see here T limits 403.6. So this is essentially a supplemental essential variable, and it basically comes in because of the code of construction, so we need to apply it. So again, we need to look at this, and then it basically tells us that the minimum base metal thickness is limited beyond that table 451 again. And the interesting thing that I like about ASME is, as a materials engineer, you can generally go back and find some understanding, or you can relate it back to base principles. Like, there is an actual scientific basis for this. So in this case, it's related to heat input. As we know, heat input has a big effect on your microstructure, which ultimately affects your toughness. So it's just limiting your ranges a little bit tighter, so you can't qualify on something thick that has rapid cooling, put that same amount of heat into a thin coupon, get a lot of grain growth, have a really wide coarse grain halves, and all of a sudden you don't get your Sharpie properties, right? Make sense? Is everyone with me so far? So once the draft is complete, welding and testing takes place as required by the code. Again, most of it's delineated in for groove welds in 455 or 451. But the other thing I want to draw your attention to is for ASME, and especially ASME 9, the groove weld is king. In the structural world, they pretty much live and die by fillet welds. They rarely do complete joint penetration. Like, it's not used as much. Whereas everything for pressure vessels piping is usually a groove weld. So you can qualify. There's a separate qualification if you just want to do fillet welds. But you can see there's a bunch of tests and you have to go a bunch through. But if you do it through a groove weld, you're qualified for everything just by doing one groove. So that's just the way ASME approaches it, is they don't give groove welds that much, fillet welds that much stick. Similarly, if you're doing special processes like corrosion resistant overlays or hard facing overlays, there's a separate qualification scheme to go through. The only thing that isn't listed on here, because I sort of cut it off, was for corrosion resistant overlays, if you specify chemistry range, either by design or on the WPS, then as your PQR, you need to actually measure the chemistry of your overlay to ensure you're not getting dilution and you have sufficient corrosion-resistant properties. So once all that's done, basically you start to populate your PQR. And PQR, as I said before, these are the actual ranges of variables that were used during the actual welding. This is a real PQR. It's basically one of the more generic ones. But you can see they listed everything right down to the carbon equivalent, which again, ASME doesn't care about the carbon equivalent unless you're doing a temper bead weld. But there's lots of other codes and standards that do. So if you don't write it in here, it's gone forever. And if a client needs it, what's your carbon equivalent? Oh, we don't have it. Well, we have to go back and now redo all of this testing just for one variable that doesn't matter per ASME, right? So that's part of the reason why you go through the draft procedures. And the other thing that's included in this is the mechanical test results. So unlike structural welding, ASME doesn't really care. ABSA doesn't really care, you just gotta get it tested, and somebody's certifying and signing off on the results. So basically, that person's on the hook. If you lied and falsified data, and you write it, something falls down, kills somebody, or blows up and kills somebody, you just go to jail for a really long time. So like I said, once that's all done, basically you write your WPS, and generally what happens is the WPS, most vendors will write the absolute maximum allowable ranges per ASME 9. That gives you the biggest qualification range, the biggest range of applications, but again, that's per ASME 9, which we'll get into in the next one when we start talking about code structure. So for pressure equipment, it doesn't matter what it is, the dominant code is the code of construction. The code of construction can be API 650 if you're building a tank. It can be B31.3 if you're doing pressure piping, B31.1 if you're doing power piping. Not to call you out, Aaron, but power piping is specific to boilers and fired heaters and things of that nature, so it's meant for higher temperature, so it has slightly different design criteria, and then also inspection and whatnot. So everything goes off of the code of construction. This applies to pipelines. And then basically the code of construction will reference the minimum requirements for design, materials, fabrication, and then inspection, but for fabrication only. So when we're talking about fabrication, the code will define it once it's in service. That's governed by whatever specific industry or governing body exists. So the one thing that I wanted to point out, so just in here, just to explain, like, as we were saying, ASME 9 would provide the basis for welding most of the time, ASME 2 for materials, ASME 4 the basis for inspection. So I just wanted to bring up a few things about ASME 2, just because it tends to get glossed over. I'm actually surprised that Aaron brought it up, because most people ignore this and they don't realize what a treasure trove it is. So there's 4 parts to ASME 2. Part A is for ferrous materials, so this covers like SA105, SA333, so the SA is simply A105, so it's your carbon steel piping. A333 is your seamless carbon steel piping for low temperature applications. Your A182 is tubular stainless products. So essentially what ASME did was they took all of the ASTM product specifications, dragged them over and put them in one spot, threw an S in front of it. I don't know what the S means, except it's ASME in this case. And those are the repository. So they said these are the materials that you can use to construct pressure equipment. And then part B is for non-ferrous, and part C is for the welding electrodes, which is a huge resource because it not only goes through the designations, it explains what E7018 means, each number means. It defines the chemistry, the minimum sharpening properties, the minimum tensile properties. It also defines how to go through and prove that your welding electrode has these properties. So if you need to prove a chemistry, then this is how you prove a chemistry. This is how you build your weld pad, limitations. It also goes through how you prove it's low hydrogen, low moisture, all that kind of stuff is in there. And then part D is the one that's most overlooked. It has all the design properties, so allowable stresses, maximum temperatures, minimum temperatures. It also has known problems. They've gone through and said, of the materials that we say we're allowed to use, these things can happen in these scenarios. You need to be aware of it. And then the other thing too is even if it's not listed in part A and B, like for pipeline steels, they'll actually go through and in certain applications you can use pipeline steels because it has ASME approved properties. So as I said before, in North America, most of the codes of construction will reference ASME for some, if not all, of the welding fabrication. So I apologize, it's blowing stuff out. I think the aspect ratio is different than on my computer at work. But this little screenshot is actually from CSA Z662. So Naren went through basically CSA Z662. They have their own qualification scheme that applies for line pipe. But CSA looked at it and said, okay, well, if you're not actually joining pipe that's going through a prairie somewhere, chances are you're going to get the work done in the shop. And if you're getting the work done in the shop, chances are they're going to be an ASME facility. So you're allowed to use ASME qualified weld procedures as long as it falls under these criteria, which is mainly listed down here. This is more design stuff. Similarly, if you look at API 650, pretty much anything that builds things that retain pressure, or even stuff that doesn't, they'll reference ASME as the fallback. The code of construction will often modify either the qualification requirements or the range of qualification. So when you're specifying, qualifying, reviewing procedures, you have to know the code of construction and the limits of application. So again, this is from CSA Z662. So we talked about how they have their line pipe one, and then they say, okay, well, if you're not building line pipe, then you can use ASME. But now they have a whole separate one that is if you're using line pipe or other stuff above a certain temperature, which I believe is 120 degrees C, it might be 200, they say, okay, well now you need to apply a separate set of criteria, which is you have to do tensile testing and report the yield strength, but you have to do it both at room temperature and your maximum design temperature. So the whole thing with this is, I can't emphasize enough, if you get one thing out of pressure piping is you have to start at the code of construction and figure out what it requires, and you have to know what the application is. If you're an engineer in the field or wherever and you didn't understand that this was running in steam service at 220 degrees Celsius, somebody would either hand you a straight Z662 procedure, which is inappropriate and wouldn't be not allowed by code, or they would hand you an ASME procedure that didn't have these extra tests, and that also wouldn't meet code. So you have to understand the application and the process. So moving on to Sharpie testing. As you may have got from Darren's talk, Sharpie testing is, it's a little bit of its own animal, regardless of which code you go to. With pressure piping, it's more and more of a concern. More steel is being manufactured from recycled materials, so like the tramp element count is getting up higher and higher. Also, there's a rush to get cheaper and cheaper materials. So as a result, like, we're not getting the same steel that they were getting in the 50s and 60s from the primary ore. So it's becoming more critical, more codes are getting more stringent in how you test it. So you have to understand basically how the code of construction approaches it, and then also ASME 9. The problem is the code of construction, which again drives this whole thing, it's not usually straightforward. Like for example, ASME 8 Div 1 for pressure vessels in non-cyclic service. It is so horribly complicated that ABSA took the time to publish a directive that's like 24 pages long that is basically summed up by Sharpie testing is complicated, but it's also really important. So like this is one of their flow charts just for materials. So it references all the clauses and exemptions and how you go back and forth to try and figure out if impact testing is required. And then once you figure it out for the materials, that informs your welding, and then that depends on your welding process and the thickness and all this other kind of stuff. The whole point is not to read this and to know it all, it's to understand that it's complicated. But if you're in that situation, you have to take a look at it because it affects a lot. So, for example, we talked about beforehand, like the maximum qualified thickness for ASME 9 is generally 2T. And this applies for supplementary essential variables unless it's something like short-sicketing MIG. So it's 2T for happy days, but then we have to know and understand the code of construction, because here in B31.3, we can see two things. If you require impact toughness, there's also really stringent testing, so you have to do one impact specimen or one set of 3 Sharpies for each type of filamental, each flux, and that has its own defined range of qualified variables. So now you're restricting each process that you're using within a larger coupon. And you also have to understand that no matter what you do, it's still limited not to 2T, but T plus a quarter inch. So you can go through your draft procedure if you don't understand that it's going to be used in B31.3. You think you have it, you've done a coupon on a half inch, you're qualified up to 1 inch, and your application's for something that's about 800 thou or 3/4 of an inch, or just over 3/4 of an inch, you go to B31.3 and you can't use it. And this has happened more than once. Like, vendors get very angry because they're like, well, it meets ASME 9. So, oh, it's one thing, sorry, it's a callback, I forgot to mention it. Once you register a procedure, I skipped over it because Darren had mentioned it. ABSA does review weld procedures, and they certify them, and they're registered, but ABSA only looks to see that it's compliant with ASME 9. They don't know what code of construction it will be used for, so they don't restrict it. So they're only gonna say it's ASME 9. So you'll have an ABSA stamp that says a procedure in our fictitious example is good to 1 inch, whereas if you try and use it to B31.3, it doesn't become. Clear? Sorry, I just forgot to, I just skipped that whole section, I deleted it when I heard you say it. So, moving on, just because you can doesn't mean you should. You've heard me say it more than once, the code is the minimum requirement. It's built to cover a variety of applications. The same ASME process piping code that is applied in Fort McMurray is also applied in Saudi Arabia. Very different temperatures, very different products, very different applications. So you have to use your engineering judgment to prevent failure in a given application. And this goes back to sort of what Naren was talking about, the difference between code standards and specifications, except sort of in the pressure piping world, or the pressure world rather, the code is the bare minimum. You cannot do less than the code, but you can do more. You can do much, much more, which is where standards come in, which can be anything from like a NACE MRO 175, which covers sour service in upstream oil and gas, to NACE MRO 103, which covers sour service in refineries. There's also specifications and recommended practices. One of the ones that I would highly suggest for a recommended practice is API RP 582, which is the recommended practice for welding in the oil and gas and petrochemical industries. NACE also has a whack of different specifications that cover welding for amine service, for caustic service, for sour service. And most of these lessons and specifications came about because things went catastrophically wrong and people usually died. So they got together and they basically wrote documents to try and prevent that in the future. Awesome, good. So, sorry that these keep on blowing up and covering off the text. But basically, one example of this is post-weld heat treatment. So post-weld heat treatment is generally not required for ASME 8 Div 1, B31.3, or Z662. And the reason why generally is in quotation marks is because the ASME codes actually require mandatory post-weld heat treatment for everything, and then they go through and list a whole bunch of exemptions that basically cover off about 90% of the applications. So it's there, but it's not there. The Z662 down here is a little bit more straightforward, where they just say basically you don't have to worry about post-weld heat treatment until you get over 1.25 inches or 31.8 millimeters. But every single code where they provide an exemption will have some variation of language that says except. And CSA is just a little bit more clear. It's like they basically say you don't have to post-weld heat treat unless you have to post-weld heat treat because of the weld properties, residual stresses, or whatnot for the intended service that you give off. So anyways, moving on to the next slide. So with post-weld heat treatment, did you guys go through much? Did Patricio talk about this? Post-weld heat treatment, welds, anything like that? So post-weld heat treatment is good for a lot of different reasons. There's a reason why it was sort of the full go-to mandatory thing. And it basically reduces the residual stresses. So you can see if you spend about an hour in your post-weld heat treatment range, depending on your thickness, you can get a 90% reduction in stress. It drives out hydrogen, allows it to diffuse out, which reduces the likelihood of stress corrosion cracking, SOHIC, a whole bunch of different damage mechanisms. It reduces hardness, which can again allow you to meet NACE or some of these other documents that have hardness controls, and it tempers some of the microstructures. So if it's so good, why are there so many exemptions? And basically it's because the code is the minimum requirement. They don't want to handcuff some guy that's making propane bottles for your barbecue to the same standard as Petrochem that's using hydrofluoric acid to crack petrochemicals to make avgas. But as a result, they don't consider the effects of a lot of processed fluids, and they also get a lot of pushback in industry because post-weld heat treatment is a cost multiplier. It adds time, it adds expense, which impacts schedules, and for the most part, the number one thing that you'll hear if you ever have to deal with this is customers will say, or vendors will say, well, it's not required by code. We don't have to do it per code. But again, as we said, the code's the minimum, they don't care. So it's left up to the designer and then also to the owner. With pressure equipment, everything, ultimately the buck stops with the owner. The owner can choose to ignore the code, they can do whatever they want essentially, but if anything goes wrong, the owner is ultimately liable. So that's why lots of owners will specify, yeah, you gotta build this, but it's gonna be in sour service, so you must build it to ASME 9, B31.3, and NACE MRO 175, which has separate restrictions for base materials, hardnesses, welding technique. Same thing with the API, like they call in different things depending on your service level. So everything's based off of the owner requirements in code.